This is the material that we had to download, so I hope all of you downloaded already. Yes? Thumbs up? Okay, good. So we need to install 3 little packages, but now all of you are experts, so it should be really easy. So you just need to write it. First, you write this one, reshape2. So install.packages, reshape2, and then the same with the other 2, one by one, only please. And please use the red stick notes if you cannot install it or you have any problem, okay? In R, so you open R, and in the console, bottom left, you copy all of this. Can people in the back? Yeah, I will. Now can everyone see? Yeah, good. Ya, mi pulso no muy bueno. How is going with the installation? Everything okay? Okay, just raise your hand if you have any problem, and also maybe if you have still the green stick note, put it in your laptop if everything is installed. Yeah, all good. Okay, so all good? Who is still not there? Raise your hand if you are still not there. Okay, we wait 1 minute, and then we move on. Yes?
Where we have to select to install?
You need to write all that put there here, but here.
Okay.
That's the console. Put it maybe maximize here. Then you have it there. So write it there. Yeah. Well, I mean, we are not gonna, because we're a bit out of time, but don't worry. I mean, it's just one plot that is gonna be everywhere. You can see it here. Okay? So no worry, there is not much to run today. It's more so you have it. Okay, I see most of you are good. So remember that you download these previous files So you put it in a folder in your desktop, you open RStudio. So remember, when you press session, set your working directory in that folder. And then open the file comparativegenomics.rmd. But no worry, today we are not going to run much. We are just going to run a couple of plots. And also they're going to be here in the script, so don't worry. Hmm? Only these ones. Two files. This one, okay, you open the comparativegenomics.rmd, and then the code should show up in the app left part. And then once you have opened, click in the env comparative genomics art data. And then it will ask you if you want to load it. You press yes, and then you will get a lot of variables and things in the app right. Okay? Okay, so I'm gonna suppose that everyone is good because we are running a bit out of time, so we want to move on. So don't worry, because all the plots are gonna be in the screen too. You're not gonna miss anything, and we just need to run little things today, okay? So we are gonna start. So please, some attention. So we are gonna do a practical about comparative genomics. That is one of the main topics that we have been doing today. Okay? So first, we have here our magic slide where we have the whole course here. So in which part are we here today? Here, comparative genomics. So first, what is comparative genomics? Well, Victor already explained it really good in his lectures, but we can define it as the process of comparing genetic material of one organism to another to better understand how a species evolve and to determine the function of genes. So two of the main objectives of comparative genomics are to see how a species evolve and also to determine the functions of different genes. So you can see it like this. Imagine that we have a present-absent matrix where we have here these shapes that are genetic materials, so some genetic features, can be different things. And then here we have 3 bacteria. So then we have a 1 if it has that feature, and a 0 if it doesn't have that feature, okay? So then what we are looking for is to see, okay, which features are common among all of them, which features are only in one bacteria, which others are only in the other bacteria. So now, after this, I want to introduce the concept of Pancor genome. You got already some ideas from Victor's lecture, but we are going to see it more visual now. So we have the same present-absent matrix here. So, but now our shapes are genes. So genes is the most common genetic feature that you are going to compare when you are doing comparative genomics. So imagine that we have, okay, we have the same Venn diagram. These plots are called Venn diagrams. So we have different concepts inside the pancore genome. First, we have pangenome. So pangenome is all the genes in a given data set. So our data set is this, and we have 4 genes, right? So this will be the pangenome. Then we have the core genome, that is the genes present in all genomes of a given data set. Wait, this died. So which one, I did a little spoiler there, which one will be the core genome here? Which shape? The triangle. Good, because it's in all of them. Then we have unique and specific genes that are present only in one bacteria of the dataset that you are using. So then, which one will be our unique specific genes here? Which shapes? Exactly, the 3 others. So this is the basic concept of comparative genomics. You are comparing genomic features that in this case are genes, and you are seeing which one is in which organism. Okay? Everyone got this? Good? Perfect. So now we're gonna get also other definitions. We have orthologs, we have paralogs, and we have homologs. So do you know which are these 3 things? 3 concepts? Probably most of you know, but we're just gonna refresh a bit. So imagine that we have an early globin gene from a really ancestral organism. This gene went through some duplication. And now we have an alpha chain globin gene and a beta chain globin gene. Then, in the alpha chain, it diverged in each organism. So we have an alpha chain gene of the globin gene in frog. We have one for humans and one for mouse. So orthologs will be the genes that are in different species, but they evolved from the same ancestral gene. Then paralogs will be the genes that they are within the same organism, for example here, mouse, and they are normally due gene duplication events. And then we have homologs, that paralogs and orthologs, they are both homologs. So homologs just wrap all of them in one concept. Okay, is everything clear? Good. So now, can we find genes potentially associated with a fungal antagonistic phenotype? This reminds you something, right? This is really similar to the practicals that you are doing. So just let's do a quick recap of your practicals that you're doing in the wet lab. So you isolate some bacteria from this soil, and then you are gonna test if it has a fungal antagonistic phenotype, right? So then you got 3 bacteria, and then you see that 2 of them